Hey there, chemists. We're going to start looking at acids and bases in this unit, and we're going to start with just strong acids. Strong acids completely dissociate. So if I have a generic binary acid like HX, we write it irreversibly becoming H+, and what we call its conjugate base, what this thing looks like without the H+. So you get a negatively charged X. The strong acids you should know are the halogen acids HCl, HBr, and HI. And then there are four other oxy acids: nitric, sulfuric, chloric, HClO3, and perchloric acid. There are other strong acids, but those are the 7 that you should know for the purposes of this class. What about weak acids? A weak acid only partially dissociates. So if I write a generic weak acid HA, it does turn into H+ and A-, but we usually write this as an equilibrium with reversible arrows. If we write it as an equilibrium, that means we can write an equilibrium constant for this. We follow the same rules: products over reactants, everything raised to its coefficient. So we get the concentration of H+ times the concentration of A-, all over the concentration of HA. This is an equilibrium constant like anything else, but because it has to do with acids, it gets its own property. We call them Ka, acidity constants, or acid dissociation constants. So let's practice that right now. For each of these, we're going to write the formula of the acid and then show its dissociation and its Ka expression. Starting with ammonium. Ammonium is the polyatomic ion NH4+. I write it reversibly dissociating. It loses one H+, and then whatever's left over. You always lose one H at a time. We'll talk later about what happens when you lose multiple H's from polyprotic acids. So how do I write the Ka expression? Ka expression would be the concentration of H+ times the concentration of ammonia divided by the concentration of ammonium. And these Kas have numerical values. They go with the acid. They tell us how strong the acid. The bigger the K, the more this dissociates, and therefore the stronger. So it's a measure of the acid strength, and it only changes with temperature. In fact, let's make a note of that back up here, because that's true for all Ks. Only changes with temperature, just like every equilibrium constant we've learned about. All right, let's try another one. This time it's a complex ion with aluminum. This is a hexa aqua aluminum 3+ ion. It's quite large, but you treat it the same way you would treat anything else. One of the water molecules that's in this ion loses one H+. We just have to write the formula of what's left. Well, we still have an aluminum, and if I picture the 6 water molecules, there's only 5 now, because one of them is no longer a water, it's now an OH. And since I lost an H+, my 3+ charge is only going to be a net 2+ in this conjugate base. To write the Ka expression, it's the concentration of the H+ times the concentration of that conjugate base, Al, H2O5, OH, 2+, close bracket. Don't forget to include the brackets, all over the concentration of the original ion, Al, H2O6, 3+, close brackets. So I'd like you to hit pause and try one on your own. See if you can figure out what it would look like for acetic acid and its dissociation constant. Okay, acetic acid is HC2H3O2. We write it reversibly losing one H+, and then acetate, C2H3O2 negative. Ka is the concentration of H+ times the concentration of acetate, all over the concentration of acetic acid. Worth knowing, you might see other representations of acetic acid in this class in addition to HC2H3O2. It's sometimes written as CH3CO2H, or sometimes writing out both O's. Those mean the same thing. The acetate is actually abbreviated as OAC, and then an H in front of it means acetic acid. So you might see those as alternative representations of just what acetic acid is. Don't be fooled, it's the same chemical compound. All right, so that's acidity constants and how we write their dissociation expressions. Let's look at our first acid-base reaction. Here's the reaction of, this is an ammonia molecule, and this is an HCl molecule. When acids react with bases, they swap a hydrogen ion. So we have a pair of reversible arrows here, and this is just a picture of what you end up getting. Looks like we get an ammonium ion and a chloride ion. And just to make sure we're clear about the terminology, the ammonia is the species which picks up an extra H. It's a proton acceptor. So that is a base. That's all bases do. The HCl is obviously the acid. That's because it is giving the H. The ammonia is taking that H from the HCl. So we're left with its conjugate. So the ammonium ion is the conjugate acid of ammonia, and chloride is the conjugate base. That's just terminology. And one more thing we'll look at, we're not going to come back to this until a bit later, but we might as well introduce it here, is the concept of predicting which way a reaction like this would go. This is a particularly strong acid reacting with ammonia, so it's going to go very far to the right-hand side. But what if it wasn't HCl and I had a weak acid in its wake? Let's change this to a HF molecule instead of HCl, which happens to be weak. And instead of making Cl minus, what if we had F minus? Now I have two things that are weak, and I'm trying to figure out which way does this equilibrium lie. Well, what we have to do is compare the strength and then the respective stability of the acid on each side of the reaction, or the base on each side of the reaction. I'll start with just the acids. We'll come back to comparing bases later on in the course. But if you compare the acids, you can look up their respective Ka values. The Ka for HF is not the same as the Ka for ammonium. The Ka for ammonium is around 10 to the negative 10, whereas the Ka for HF is around 10 to the negative 4. Had to look that up just for a second there. Now, this right away tells us who's stronger. The higher the Ka, the stronger the acid. Let's make a note of that. Higher Ka equals stronger acid. But sometimes chemists don't like to look at Ka numbers because they're always these small powers of 10, and it's easier to compare just integers. So we often take what's called the pKa, and the pKa will be lower for a stronger acid because the pKa is the negative logarithm of the Ka. We're just changing a number to a different number mathematically. So the pKa of HF is around 4, and the pKa of ammonium is around 10. So we still have a stronger acid of HF compared to ammonium because it has the lower pKa. But what nature really cares about is whichever side leads to the more stable side. And the more stable side is weaker. The weak shall inherit the earth, because weak things are not reactive, aka they are stable. So stable is another way of saying weak in chemistry terms. So that means I'm going to lie very much toward the weaker side of this reaction. So I could even approximate the K value for this, but I'm just going to put on top of this reaction a net forward arrow, meaning the products, what we've written on the right-hand side, predominate in this reaction. We'll come back to more acid-base reactions later, but this was just a good opportunity to interject one acid-base reaction and how you can actually predict who is the weaker species. This also tells us that fluoride is a more stable base than ammonia. If we looked up their Kb values, we would see the same thing is true. Okay, so let's wrap up with a couple of other definitions and then a few calculations in this acid-base intro lesson. Sometimes we have species that act as both acids or bases, and we call these things amphoteric. Water is the best example, but there are many other things that are amphoteric. For example, any polyatomic ion that has an H in it, such as the bicarbonate ion, can count as an amphoteric species. So HCO3 minus, I'll put another one, hydrogen sulfate is amphoteric. That should make sense because they can both lose an H, they have an H to give, but they're negatively charged, so they can also gain an H. So this could lose an H to become CO3 2 negative, or it could gain an H to become H2CO3. In other words, it can act as an acid or a base. Likewise with HSO4 minus as well. Some interesting examples, certain metals like aluminum metal can actually be amphoteric. You can make an aluminate ion or the aluminum cation in acidic species. It reacts with both an acid and a base. Water is the most common one, so let's look at how that behaves. If I have a water molecule and I want to show that it's behaving as an acid, that means it can react with a base, for example, ammonia. And this would be written as a reversible reaction. If water is acting as an acid, that means it loses one of its H ions to become OH minus. And then you would get the conjugate, NH4 plus. This is actually the Kb expression for ammonia. That's actually how you write it. Ka always makes H plus, Kb always makes OH minus. Acting as a base, that means water would react with something that's an acid. So let's say I have water reacting with HF. Reversibly, that would form H plus, or actually hydronium, and then fluoride. And this, likewise, is really just the Ka expression for HF. It's what this looks like when it dissociates into a hydrogen ion and its conjugate base. Water can even be amphoteric with itself. This is called the auto-ionization of water, and we write it as a water molecule reversibly becoming an H plus ion and a hydroxide ion. Sometimes it's written as two waters becoming a hydronium and a hydroxide, but that's just a simplification of the same thing. And this reaction is so well studied, it has its own K value. It's called Kw, and it is the product of the hydrogen ion concentration and the hydroxide ion concentration. And at 298 Kelvin, this equals 10 to the negative 14. Like every other K value, it changes with temperature, but there's always both hydrogen and hydroxide ions present in everything that's aqueous. If you have more hydrogen ions, you're acidic. If you have more hydroxide ions, you're basic. And if you are equal to each other, you are neutral, and that's summarized over here, off on the right. All right, let's wrap up with some numerical things. This is supposed to be a review of things you might have done in an intro chem class, so we're racing through intro to acids and bases before we get to more applications of them. In the lower right of your notes is an equation summary table that reminds you how to get pH and pOH, likewise Ka values as logarithmic. At 298 Kelvin, the sum of pH and pOH is 14. That's really only at 298 Kelvin. And then there's the Kw expression we just learned. This equation, called the Henderson-Hasselbalch, we'll get back to later. Just tuck it under your hat for now, and we'll come back to that when we learn about buffer mixtures. Okay, so let's say I want to find the concentration of an acidic solution or a basic solution. We usually use pH to determine this. So the first one shows me 0.1 molar nitric acid. This is strong. So my concentration of H plus is equal to the concentration of the nitric acid, which is 0.1 molar. So the pH is just the negative log of 0.10. And when you take the negative log of a tenth, you get 1. And you could write it as just 1. There's a rule for sig figs regarding logarithms, since they're base 10. The number of sig figs in the molarity will actually become the number of decimal places in your pH. So you would see this reported as 1.00, meaning 2 decimal places in the pH goes with 2 sig figs in the molarity. It's okay if you don't stick to that rule, but it might explain why some of the answers are what they are. So that's boring because it's easy. Getting the pH of a strong acid, that's simple. A weak acid is a little more interesting. Weak acids, we either know from the formula or because we're given a Ka value, they have a dissociation. So HF dissociates into H plus and F minus. And now that I have a K value and an equilibrium and a molarity, or essentially an initial molarity, I'm going to set up an abbreviated Rice chart for this. With 1 molar HF, we're going to lose some amount of it, and we're going to gain some amount of hydrogen ions and some amount of fluoride ions. So my K, 0.00072, is equal to the expression H plus times F minus all over HF, all to the first power. That's x squared divided by 1 minus x. Now K is small, so we can assume that however much of this 1 molar I lose to make these respective species, it's potentially negligible compared to the initial molarity. So we're going to abbreviate this, just like we did with certain other equilibrium problems, as just x squared over 1. So all I have to do, because it's 1 molar, is take the square root of the K value. So 0.00072 to the 1/2 power gives me 0.027 molar. And I'm going to remind myself that X is my H plus concentration. If this was a Kb expression, my X would actually be an OH minus. But here it's a Ka, so X is H plus. So to get the pH, I just take the negative log. So the pH is the negative log of X. So the negative log of that number, I get about 1.57. Okay. So that's how we get the pH of a strong acid and a weak acid. Let's do one more that I want you to try. Here's a weak base with a Kb value. See if you can figure out what the equilibrium expression looks like for this Kb of ammonia and how you use that to ultimately get the pH of a 15 molar ammonia solution. Okay, so ammonia doesn't have a hydroxide in it, but we have to somehow create hydroxide. That's what's always going to be true for anything that has a Kb. That means you have to include a water molecule on the left-hand side of your equilibrium, and that's how you end up making ammonium. That's what the Kb equilibrium expression looks like. That's the reaction that it goes with. I don't care about the water molecule for the purposes of K because it's a liquid. It doesn't go in the expression. So I still care about just these three things, just as if it was a weak acid. I have 15 molar ammonia. I'm going to lose X. I'm going to gain X of the hydroxide and X of the ammonium. So 1.8 times 10 to the negative 5, my K value, is X squared over 15. We're going to take that assumption that X is small. You solve for X on your calculator. 1.8, 10 to the negative 5, times 15, take the square root, and I get 0.016. And here I'm going to remind myself that's a molarity of hydroxide. So I have to turn this into a pH. Well, the first thing to do is turn it into a POH. So the POH is going to be the negative log of x. So I take the negative log of that number, and I get 1.78. And then my pH is 14 minus the POH. We'll assume that we're at room temperature. Didn't tell us that, but that's a safe assumption. That gets me a pH of 12.22. And a good self-check is to say, well, we are in base, so my pH better be big. It's pretty concentrated, but it's still weak, so that pH sounds pretty sensible. All right, I'll just wrap up with one last thing that I'm going to squeeze into the margin way over here that has to do with when can we make this assumption? When is it safe to do this? And to remind you of what we saw in the equilibrium unit, it depends on what's called the percent ionization. The percent ionization is equal to whatever you end up calculating as your value of x divided by the molarity of the original compound. In this case, I'll just say HA. And then you multiply that by 100. As long as your percentage is less than 5, you're okay to use that assumption. That's sort of the general rule that we have in this course, and I've seen that in many textbooks, so we'll stick to that. So I could even check some of these. Is my percent ionization for this problem within 5%? Well, we get 0.027 divided by 1 and then times 100. Yep, that's 2.7%. We are okay with that. I could even check the one that we just did. 0.016 divided by 15, multiply by a 100. Oh yeah, you're definitely within 5%. All right, so that's how we calculate pH for weak acids and strong acids, as well as a base, and a general overview of just how we deal with acid-base equilibria.